Hello and welcome to this series of an overview on precast construction technology, a Lego construction. So in this series we have already seen various elements starting from precast hollow core slab. Then we have also seen precast wall panel, precast and pre-stressed beams. Then we have already also seen the precast column. We have seen precast landing and staircase, as well as we have already seen the load test on hollow core slab. So in this video our main scope will be the calculation of the pre-stressing force and its calculation of elongation. So the calculation of the pre-stressing force and elongation is very important when we are doing any pre-stress element. So let me clear you that there are two types of precast elements, that is known as it has type 1, which is known as pre-stressed element, and second is known as the post-tension element. Pre-stressed element means the strand wire is used in both of the case, but in pre-stress the thing is that before doing the concreting, the wire is stressed and then the concreting is done. So that is known as pre-stressed. And post-tensioning is that in which the duct is used in the profile that is set in the mold during the mold preparation and cage placement, and then the concreting is done, and after achieving certain strength, the strand wire will be passed through the duct that is placed into the element, and then the post tensioning is done according to the design force that is given. So there are total two types we have this seen. So in this video we are talking about pre-stress force and its calculation, and we will also see how the elongation is measured and its standard code that is used for the calculation. So here you can see the graph. We have the graph for reading versus elongation. So we will also see what is this and how it works. And here we have the formula for elongation, that is elongation is equals to P into L upon A into E. That is, P is the force, L is the length, that is jaw to jaw length, where lock is fixed on the both of the ends, A is the area, and E is the modulus of elasticity. So we will see how this calculation is done using IS 14268 2022. So here in the left hand side figure you can see this is the pre-stressing gun that is used, and these are the strand wires that are used. This all are the strand wires. This is the pre-stressing system in which the strand wires are stressed before the pouring of the concrete. And here you can see these are the wedges and barrel. We will also see in our further slide how wedges and barrel are and why it is used. So basically this is the anchoring structure. So you can see this is the strand wire, and strand wire is locked using the wedges and barrel over here. And similarly on the other hand, which will be on the back side, here also same wedges and barrel will be used to lock the wire. So let us move ahead and let's see the IS code. So the IS code which is used for the calculation of the pre-stressing force and its elongation is IS 14268 2022. So here you can see this is the Indian standard, that is IS 14268 2022, and it is for the we can say uncoated stress relieved low relaxation 7 ply, or we can say 7 wire ply strand for pre-stressed concrete specification, that is revision 2. So here you can see this is 7 wire ply. What is 7 wire ply? So if you check this figure, that is figure number 1, so this is the strand wire. Here you can see this is the strand wire. So strand wires are made with the number of wire. So here you can see there is a wire, so it is a 7 ply, or you can say there are total 7 wires that are twisted, and it has a center wire, and these numbers of wires will create the strand, and when the numbers of strands are twisted together, that is known as tendon. So this is the concept. So the first individual, it is a wire that when seven numbers of wires are twisted and created one wire, that is known as the strand, and number of strands when twisted and created uh, another wire, that is known as tendon, or we can say rope. So now coming on to the terminologies. So as per the IS 14268 2022, there are some of the terminologies that are very important to understand before forward. So first thing is the breaking load. So that says that that is the maximum load reached in the tensile test of the strand. So breaking load is that when we perform a tensile strength test on the strand wire, so the maximum load at which the strand wire breaks is known as the breaking load. This all terminologies will be important, and it will be used in the calculation of the pre-stressing force and its elongation. So second terminology, we have coil and reel. Coil and reel means one continuous length of the strand in form of coil or reel. So it's basically we can say it's a reel, or we can say it's a longer length of the strand wire uh, that is covered, or we can say that is bundled in one of the coil in form of coil, and it is used for a continuous length. Third, we have the elongation. What is elongation? So elongation is the increase in the length of the tensile test piece under stress. So elongation means when we apply a force, or we can say when we apply a tensile force on the strand wire, then it increase in the strength due to the force. So that increase in length due to the force, that is known as elongation, and this elongation we used to measure while performing the pre-stressing uh, while doing the application of the pre-stressing force. Then we have length of lay. What is length of lay? Length of lay is the distance measured along to the straight line parallel to the strand in which a wire form one complete helix. So that means when we let's say we have taken a 1 meter of strand wire, so we will measure that distance and it is 1 meter. So that length in form of twisted is known as length of bay. Similarly, you can go through all these parameters as well. So parcel, and we have production length, proof load, that is 0.2% of the original gauge length. Then we have what is 7-ply strand. So we have already discussed that what is 7-ply strand, indented strand and compacted strand. So there are total two types of strand that we will discuss in this video. So here you can see indented strand and we have compacted strand. So let's move forward. And so here, as per IS 14268 2022, you can see the table number 2, which says about the strand dimensions and physical properties. So you can see the clause number 5, that is point number 6.1 and point number 6.2.2.1 as well as 2.2 as well as 2.3. So you can check that the specifications, or what is the strand dimension and its physical property. The description has been given over there. And so let us come back to the table number 2, that is the standard dimension and the physical property. So here you can see in the column number 2, it says that the strand designation, which means in the first thing that you see is the diameter of the strand wire. Second is the tensile strength, or we can say tensile capacity of the strand, and this we can say type of the strand. As we have seen in our further slide, that there are two types of wire. So here you can see compacted wire, which means C, this is the compacted wire, this is indented wire, and there is one more type which is known as plain wire. So there are total three types, which is I is the indented, C is the compacted strand, and we have P, that is plain wire. So here you can see the first thing. So in the column number 2, that is strand designation, this is the diameter of this strand, which says 15.2 mm. diameter of the strand wire. Second is the tensile capacity or tensile strength of the wire, that is 1670 Newton per mm square. And this is this type of strand, which means P. P stands for plain wire. So coming on to the column number 3, as we have already seen that this is the diameter of the strand wire, this is 15.2 mm. Column number 4 is the tensile strength or tensile capacity of the strand wire, that is 1670 Newton per mm square or MPa. Then column number 5 shows the cross section area of the strand, that is 139 mm. Then we have column number 6 that shows about the mass per meter, or we can say weight per meter, that is in gram. So that is 1 meter wire weighs 1.086 kg or 1086 gram. For particular 15.2 mm dia with 1670 Newton per mm square capacity, it has a mass of 1086 gram per meter. Here it shows, column number 7 shows the tolerance on nominal mass per meter. So tolerance can be allowed plus or minus 2%. So here we can see this is the minimum breaking load that we have seen. Okay, so this is the minimum breaking load, that is 232 kilonewton. That is the minimum breaking load that is specified for strand 15.2 mm diameter. And we have minimum 0.2% proof load, so that is 204 kilonewton. So here you can see in other rows, this all rows that there are different diameter. Let's say this is 18 mm diameter with the tensile capacity of 1670, and it is a plain wire. Similarly, you can see this is the 11 mm diameter of the strand wire with the tensile capacity of 1770 Newton per mm square, and it is a plain wire. So it depends upon the strand wire, what kind of strand wire you are using. Let's say that you are using 12.7 mm diameter of strand with a tensile capacity of 1860 Newton per mm square, and it is a compacted wire because it is C. So here you can see highlighted in the green box. Let's say we are using that particular type of strand wire, so we will see the data depending upon the specification of the wire. So we will see the one of the example using this data. So let's assume that we are using a strand wire which has a diameter of 12.7 mm, and it has a tensile capacity of 1860 Newton per mm square, and it is a compacted type of strand wire. So let's see, this is the diameter 12.7, we have 1860 Newton per mm square as a tensile capacity, we have a cross section area is 112 mm square, we have a mass of 874.7 gram per meter, and we have a tolerance of plus or minus 2%. We have a minimum breaking load as 108 kilonewton, and we have a minimum 0.2% proof load as 183 kilonewton. So let us see one example in which we will use the same data that is highlighted in the green box. So these are continuous of the table in which the tensile capacity is changed 1960, and it is a plain wire. So it depends on what kind of wire do you use. So currently we will see one example in which we will use compacted wire with 12.7 mm diameter and its tensile capacity 1860. So, and one more thing, the modulus of elasticity that is considered is 195 GPa, that is as per IS 1343, that is suggested by the IS code, that the modulus of elasticity for the strand wire has to be considered as 195 GPa. So we will consider 195 GPa as the modulus of elasticity in our further slides, and we will see where this modulus of elasticity will be used in our calculation. So let us start the calculation of the pre-stressing force and the elongation as well. So here we have some of the data and assumptions, as we discussed in our further slides, that we have assumed that we are using 12.7 mm diameter of this strand wire, and we are using compacted strand. So the design force that is given by the designer is, let's say, 120 kilonewton is the design force for the, or we can say this is the force that has to be applied on the strand wire. Okay, so we will see how this will be used in our calculation. So the tensile strength, we are assuming that 1860 MPa is my tensile strength of the strand wire. So now let us come to the step number 1, in which we will calculate the percentage of the pre-stressing force. So the formula for the percentage of the pre-stressing force means force upon breaking load. So what is force? So the force we have already here. So the force is 120 kilonewton, that is generally given by the designer. So our force will be 120 kilonewton. So we have used force as 120 kilonewton, and here it is mentioned breaking load. So we will check the table in which we have 12.7 dia strand wire, we have 1860 as a tensile capacity and compacted strand. So we have the minimum breaking load as 108, and we are using 208, and we are using 208 as a breaking load in 200. So we will get the percentage, which means it is 58%. So it shows that how much percent of pre-stressing force is applied. This percent shows that it is this shows that it is 58% of its total tensile strength. So we are not applying 1860 Newton per mm square as a tensile force, but it is 58% of its capacity. So it shows the percentage, how much percent force we will apply on the strand wire. So it is said that it is 58%. So now let us come on to this step number 2, in which it shows pre-stressing force, that is P. This force is the another force, that is the force on the wire. Now we are going to check the pre-stressing force, how much force we have to apply, because it depends upon the jack area, which means jack area means in our first slide we have seen that we used to use the jack. This is the gun that is used, pre-stressing gun, in which will be used to pull the strand wire. So this area matters. So this area is very important while calculating the pre-stressing force. So here what we have done is like pre-stressing force P is equals to force upon jack area. So let's say the force is 120 kilonewton, that is already given by the designer. So it is converted into Newton. So we have multiplied that force by 1000 divided by jack area. So here jack area is 3768 mm square. So let me explain how this jack area is taken. So while using when you are using the particular gun, pre-stressing gun, or pre-stressing equipment, so on the equipment it is the area of the jack is mentioned. So in my case I am using 16-ton pre-stressing jack, and it has an area of 137.68 centimeter square. So while I am converting into mm square, it will be 3768 mm square. So the step number 2, pre-stressing force P is equals to force upon jack area. So force is 120 kilonewton in 2000, which will be converted into Newton, divided by jack area, that is I am using 16-ton pre-stressing force, that is 3768 mm square. So now I have received an answer of 31.84 Newton per mm square that has to be applied on the wire while stressing the force. So let's say in case of bar, so I want to let's say there are many machines that calculates the force in unit known as bar. So I need to convert this 31.84 Newton per mm square force into bar. So generally 1 Newton per mm square is equals to 10 bars. So what we have to do, we have to multiply the 10 with the Newton per mm square, so we will get 318.4 bars. So either you can use, so if in, let's say you have a pre-stressing machine that shows the force in terms of Newton per mm square, so we will use 31, we will set 31.84 Newton per mm square as our force. Or let's say we have a machine in which it shows the unit in bars, so we will set 318.4 bars. Now let us come to step number 3, which is the very important, which is known as the elongation, that is denoted by small e. As we have already seen our further slide, what is elongation? So elongation is the change in length after the application of the pre-stressing force. So what is the formula? So coming on to the formula, elongation small e is equals to force into bed length divided by area of strand into modulus of elasticity. So force, we already know force is 120 into 1000, so we have converted that force into Newton, divided by multiplied by bed length. What is bed length? So here you can see in the figure, let's say this is one of the end and this is another end, so we can also say one is dead end and one is live end. So here the wedges and barrel will be locked, point 1 and point 2 here. So here you can see this is the wedges and barrel that is used. Here is the figure of the wedges and barrel that is used to lock the strand wire. So this is the anchoring structure. Here you can see this is our anchoring structure and this is our anchoring structure. So distance between two anchoring structure is known as the bed length. So here we have the bed length of 150, so we have considered bed length as 150 meter. It is in meter, divided by area of this strand. So here we will consider area of this strand. So let us come to the table in which we are using this particular type of strand, and we have the area of strand as 112 mm square as the area of this strand. So we are using 112 mm square as the area of this strand, and we have the modulus of elasticity, that is 195, that we have already discussed in our further slide, that the modulus of elasticity has to be considered as 195 GPa. So we are using this 195 into 1000, which will convert into Newton per mm square. So here you can see we have got the answer as elongation as 0.824 meter. So I am multiplying that by 1000, so that will be converted into mm. So we have the elongation value as 824 mm per wire. So what it says, that when we apply a pre-stressing force of, let's say, 318.4 bar per wire, then the elongation after the application of the load shall be 824 mm, or plus or minus 2 mm is the tolerance. So this is how the elongation and its force is calculated for the application of the pre-stressed elements. So this was all about the calculation of the pre-stressing force and elongation. Hope you have got clear this calculation, and you have understood how the calculation is done, and it's important of the table and its properties as well. So if you haven't watched my another videos, which is on hollow core slab, we have pre-stressing wall, we have another videos on this series, such as precast landing, staircase, load test on hollow core slab. So I'm just making another videos on another technologies as well. If you liked this video, then please share me a thumb and comment below if you want similar kind of videos. Thank you so much for watching, and I will see you in the next video. Thank you.